Hi guys, let's find the total capacitance in parallel combination. Suppose if I take three capacitors, these capacitors are having capacitance C1 and another is having capacitance C2 and another one is having capacitance C3, and you always remember this formula. So C equal to Q upon V, charge per potential. Now they are connected in parallel. So in the parallel combination, so first of all, what is a parallel combination? Now here we can see, so all the three capacitors are kept at parallel, side by side. So if you can see one, another is a parallel to another, another is parallel to another. In parallel combination, the key point we remember, suppose if I can call this capacitance C1 plate A, the another plate B, and the capacitance C2 also, this is I can call first plate as A and the second plate as B, and this is also A and the B. And if you can notice it here, all the A plates of C1 and C2 and C3, they are connected to battery positive potential. So the same positive potential will goes to capacitance plate A, and the same potential goes to plate A of the capacitor C2, and the same connection goes to capacitor C3 to plate A. So likely if you can notice at here down, the negative terminal of the cell is connected to the all the B plate of the C1 and C2 and C3. So in a simple manner, if I draw the same circuit diagram, suppose these are the three capacitors in parallel. I would like to draw as a straight parallel, so that is easy to understand. So this is the capacitance C1 and the capacitance C2 and the capacitor C3. We need to connect all the plates. So I can connect the first plate of the capacitance C1 and the samely the first plate of the capacitor C2 and the first plate of capacitor C3 together. And likely we connect the second plate of capacitor C1 and the second plate of capacitor C2 and the second plate of capacitor C3. Now to this, if we apply a potential difference, so here I can take a cell or battery here. If we connect it, now if you can closely observe, the positive potential of cell is all applied to the first plate of each capacitor, and similarly the negative potential of the cell is connected to the second plate of each capacitor. Now this combination is called as parallel combination. Now in parallel combination, so we need to look more careful about potential. So let me take voltmeter. So let me measure the voltmeter at the cell first. So cell potential difference, if you can on the cell, so the cell potential difference shows at 1.5. So that is the potential difference of the cell. Now if we connect the potential difference to measure the potential difference between the plates of a capacitor C1, now the capacitor potential difference, if I can call for the cell, this potential difference also 1.5 volt, and the capacitor potential difference, it is also showing the potential difference of 1.5 volt. Now likely if you can measure the potential difference between the capacitors, between the plates of a capacitor C2, it is also showing the potential difference 1.5 volt, and likely you can measure the third C3 between the capacitor, the potential difference, it's also showing the potential difference of 1.5 volt. Yeah, it's a having common potential. Why it's having common potential? Because we connected all plates. We connected the all plates of one positive terminal of the cell and all other plates of the capacitors to the negative terminal. So here in parallel combination, the potential difference is same. So that is a very important statement I can make it here. In parallel combination, sorry, in parallel combination, potential difference is same. Now, if the potential difference is same in parallel combination, what will change? Suppose if I write the capacitance formula for C1. So for the C1 I should write similar at here. If the C1 is equal to Q upon V, the potential is always common for the parallel combination. So for the C3 is also the potential is common. But here we are mentioning there is a change in the capacitance. If the C1 is changes, so if the V is common, so there will be charge will be changes. So for the parallel combination, we will represent C1 equal to Q1 upon V and the Q2 upon V and the Q3 upon V. If we connect the capacitors in parallel. Now, there is no potential difference in the parallel combination, but there is a capacitance difference is there. So that capacitance difference comes due to because of the charge difference between the individual capacitors. Suppose if I see at here, what is the total capacitance with the help of the here the I'm having total capacitance meter. First we see the capacitance of the individual capacitor equal to 1 picofarad. Here the C1 equal to 1 picofarad and the C2 also 1 picofarad and C3 also 1 picofarad. But here we can see the resultant capacitance. So here the resultant capacitance is showing that 0.30 times 10 power minus 12 farad. So this is also I can write that 3 times 10 power minus 13 farads. So you can write that 3 picofarads. So in the parallel combination, the total capacitance. So if you can write capacitance in parallel, the capacitance in parallel equal to C1 plus C2 plus C3. Now if you can write the total capacitance at here, so we need to add the capacitance of the individual capacitors. So to do that, so we would do the little mathematics with the help of the mathematical expressions. We will derive what is the expression for the total capacitance of a capacitors when they are connected in the parallel combination. Suppose if I take, this is the setup. Now let me do the circuit connection first. So here I'm having the three capacitors. So this is the capacitance C1 and C2 and the capacitance C3. And we need to connect them in the parallel combination. So all terminals are the connected. All the first plates of the capacitors connected together, and likely all the second plates of the capacitors connected together. Now we need to apply potential difference between them. Now if I take the connection at here to apply the potential difference with the help of a cell, so this is the potential difference of the positive potential and the negative potential. The same positive charge accumulates at here because they all connected together. So all the plates, so they accumulate the positive charge. and the opposite to it here, so they accumulate the negative charge. Since they all are having a common potential, because if you can measure the potential difference at here, so the potential difference remains same. So if the potential difference remains same, so they are having the difference in charge, so that I can mention it here the q1, which is the positive q1, likely negative q1. So here at here positive q2, at here the negative q2, positive q3 and the negative q3. Now if we can write the total expressions, so the total expressions if we can write as by considering the capacitance and the charge potential relation, so C equal to Q upon V. So likely if you can mention, so this is the basic formula to write the expression. So for C1 if we can write, for C1 equal to, since the potential is common, so here it is upon Q1 by V1, so Q1 by V. So likely for C2 equal to Q2 by V, and for the C3 equal to Q by V, sorry, Q3 upon V. Now if we can combine these two, to combine, so I can take the statement at here, the total charge in the combination is, if we can take the total charge in the combination Q equal to sum of the individual charges, which are equal to Q1 plus Q2 plus Q3. Now from the above expressions, if we write that the total charge equal to, so Q equal to, in the place of the Q1, since C1 equal to Q1 by V, that implies Q1 equal to C1 times V. So I can write that expression as C1V, likely C2V plus C3V. So the Q here we will replace to find the total capacitance. For the parallel combination, the resultant capacitance C suffix P, if we can take, C suffix P is the total capacitance for the parallel combination, which I can write that total charge. So if we can mention it is the total charge Q total. So here also I can take the total charge on the three combinations upon the potential difference V. So in the place of the Q total, we will rearrange these expressions. I can mention this as capacitance in the parallel P times V equal to C1V plus C2V plus C3V. Now you cut that common factor. So here the common factor is the potential is same common on the both sides. Now the total capacitance C P equal to parallel combination C1 plus C2 plus C3. So let's see the combination for the example. Suppose if we take a net there, if the C1 equal to C2 equal to C3 equal to 1 picofarad, what is the total capacitance in the parallel? So in the parallel combinations, we need to mention that the total capacitance in the parallel Cp equal to C1 plus C2 plus C3. Just add up 1 picofarad plus 1 picofarad plus 1 picofarad, which gives the total capacitance in the parallel. So the total capacitance in the parallel equal to 3 picofarad, which gives very simple expression when we connected in the capacitors in the parallel combination. So likely at here if you remember the capacitors in the series combination. So in the series combination 1 over series, 1 over series, or this is also if you can write simply as 1 over C suffix S. So that is easy to remember. 1 over CS, S goes to series, equal to 1 over C1 plus 1 over C2 plus 1 over C3. So by using these two formulas for the series combination and the parallel combination, so we will find the resultant capacitance for a given combination. So by solving problems, we will get better understanding how a capacitance value increases or decreases by combining more capacitors either in series and the parallel combination.